Hi, NA Physics, it's Mr. Neff. Let's talk diverging lenses now. And before we do, did you hear about the man who got hit in the head with the can of soda? I'll tell you about him at the end of the video. On a ray diagram for a diverging lens, it's going to be pretty much the same thing as you did with mirrors, except you're going to have two focal points to deal with instead of one. Now, I'm starting off with the diverging one because I think this is very, very easy to draw. I'm encouraging you to draw the parallel ray first. It's easy to draw the parallel ray because I told you what the parallel ray did before. I'm going to scroll back to what I showed in the other video. Remember these two pictures. This one's important for the diverging ray. This shows you what happens to a parallel ray. Any parallel ray, all four of those were parallel. They all came in to the lens and then they were refracted as if they had come from the focal point. That's not what happens with a converging lens, and we'll do that in the next video. But for now, for a diverging lens, they come in parallel, they go out as if they had come from the focal point. So you can see exactly what's happening here. So look at this orange one. So from the end of the object, the orange one's coming out, it's parallel to the principal axis. We still have a principal axis, and it's parallel to the principal axis, and then hits the lens. Now here's one weird thing. You and I know that refraction only happens at interfaces. And so technically, the refraction happens a little at the first surface and a little at the second surface. But nobody ever draws it that way. What is drawn is you just draw it happening right in the middle of the lens. Now, ironically, that is where no bending happens because it's not an interface. So whatever angle the first surface shoots it into the glass, that's what it's going to maintain until it gets to the other surface of the glass. That said, that's just never the way it's drawn. It's drawn doing all of its bending at the middle rather than a little and a little at the edges. Now, was this drawn to refract out? Well, see what the artist did here. They drew it so that it looks like it had come from the focal point. And so they lined up their ruler on the focal point and that spot right there where the parallel ray hit the lens, and they drew it out along that line. Okay, now I said you have two focal points to deal with, and you use each focal point one time. Not one focal point twice and the other focal point not at all. Use each focal point one time. This focal point has already been used to draw a ray, and so I'm not going to do it again. So when I go to draw the focal ray, I'm going to draw the ray that comes off of this object and is headed for the other focal point. So it's a common mistake is to line up this spot and this focal point and to draw something down here like this. Not only because that's crooked, it's wrong, but it's wrong because fundamentally because you're aiming at the wrong focal point. Get rid of that. No, what I want to do is I want to aim at this other focal point. So you can see what they did here. They drew this, aimed at the other focal point, and then it comes out parallel to the principal axis like that. Okay, so that's our focal ray. Now, it's a common mistake too to get confused with a mirror, and I can't tell you how many times I've seen somebody draw in like that only to then draw out here like this. And yeah, a little bit of reflection does happen, but that wouldn't happen like that because you'd have to have angle of incidence, angle of reflection the same. And besides, this isn't a reflection thing. So no, that's not so good. We're talking about the part that's transmitted through the glass. So what I drew up here is pretty good. Now, the chief ray is slightly different because we still have this spot right here, this vertex. Now, this vertex is where the principal axis meets the lens. And we kind of consider the lens to be that line, even though nothing was really happening at this hourglass-shaped glass itself. Still, this spot right here is still that vertex. And so we're headed from the end of the object right to the vertex. And we're going to just keep on going straight. And so you can see the way this blue one was drawn. It was just drawn straight out that way. Okay. So again, you have this parallel ray leaving parallel and then going out, bending the way that the picture showed you what happens to all parallel rays. On a diverging, it is bent as if it had come from the focal point on this left side. If this were a converging lens, like you'll see in the next video, it'll go to the focal point on the far side. And then you have the focal ray, and the focal ray goes to the unused focal point. So we already used this focal point, so we're going to use this one. We're going to head for that focal point, but in the meantime, we're going to hit the lens, and then we're going to refract so that we're parallel to the principal axis. And then you're going to have the chief, and the chief is going to go through that vertex, and it's not going to change direction. It's just going to keep on going because it has no angle of incidence, and so it has no angle of refraction. Now, the place where those three either cross or seem to cross, that's where the image is going to be. You can see that these three over here, the blue, the purple, the orange, they're never going to cross. They are going to just, as you keep going farther and farther over here, they're just going to get farther and farther apart. So the observer who's over here looking at all of this stuff is observing these, and now they're saying, well, those are never crossing, but they're all carrying the same image, so that means they must have all come from the same place. Remember, why does any of this work is because we think that light travels in a straight line, usually does, except for a case like this when it's not. We take those rays and we extrapolate them back. And so you can see that this one has been taken back, dot, 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 dot. Same thing as before. We are using dotted lines for imagination. Solid lines are real light. Dotted lines are your imagination. Here comes some imagination on the focal. And the chief, it doesn't really need imagination, but it does kind of need imagination. It's going along its own line. And where those cross is right there. And there's where I have my image formed. Now, just like with mirrors, we're going to ask questions about the image. We're going to say, what kind of image is it? Is it a real or is it a virtual image? Is it an upright or is it an inverted image? Is it a magnified or is it a reduced image, or does it happen to be an image that's exactly the same size as you started with? What's the magnification? What's the DI, the DO, the HI, the HO, the magnification, all these things. And you can kind of guess as to what they are here just by looking at a well-done picture, but we can also use the equation to get the picture too. And when I say the equation, it's going to be that same old 1 over F equals 1 over DO plus 1 over DI. You might say, wait a second, that was for mirrors. That was the mirror equation. You're right, but it also is the thin lens equation, and it works for a thin lens too. Thin as long as the thickness of the lens isn't very much compared to the diameter of the lens, and we will never have anything quite like that. I just threw a few numbers on here. I say that the DO is 10 centimeters, the focal length is -5. This is an important point, and I'm not going to slough over this. If you have a diverging lens, it's going to have a negative focal length. If you can remember, the diverging or the convex mirror also had a negative focal length. Its focal point was behind the mirror. Well, we say that this diverging lens is going to have a negative focal point too. So anytime you see that diverging lens, you know negative focal length. And then the height of the object is 3 centimeters, and I'm asking for the DI and the HI. So before we actually do it, what are some good estimates? What are we shooting for here? All right, so the DO is at 10 centimeters. Can you see that in the picture? The DO is 10 centimeters. It's that distance right there, 10 centimeters. The focal length is a -5. So strictly speaking, you're looking at this focal length right here, and you're saying that that's a -5. It's using the same sign convention as the DO, and so it's on the other side of the lens. The HO is the 3, and so this is the 3 centimeters right there. There's the HO. And now what about the DI? Well, the DI is this distance right here in the picture. There's a DI, and it's on the other side of the lens than the observer. And so I know that's going to be a negative something. We'll see what it comes out to. If that green one was 10, this might be like -3 or 4. Not 5, because there's what a focal length is. That's 5. So maybe -3 or 4. Maybe it's even like 3 1/3, something like that. It just kind of looks that way. And the HI, that's the height of this object, or height of the image. So maybe that's this part right here. I don't know. Maybe if that brown one's 3, maybe this is 1 or 1.5. Let's see what we have here. All right, so if I want to solve for, let's solve for the DI first. So the DI, 1 over the focal length equals 1 over DO plus 1 over DI, and I'm going to rewrite this for 1 over DI is 1 over focal length minus 1 over DO. So how about 1 over -5 minus 1 over 10, +10. The negative comes from the equation, from the algebra. That 10 was positive, and so I'm going to make, what's that? That's -2/10 and -1/10. 1 over DI is -3/10. Don't forget to take the reciprocal at the end. DI looks like it's -10/3 or -3.33 centimeters. Looks good. Now, for the HI, and they didn't ask, but what about the magnification too? Just like before, magnification is hi-ho or negative dido. And so I already know the di and the do. I could say that the di is -333 centimeters by the do is +10, and so that looks like that's 1/3. It's positive too. It doesn't have a unit on it. That centimeters, numerator denominator canceled. Remember, it's just a ratio. It's just a factor that you're going to multiply the object by to get the image height. So +1/3. That positive tells me that it's upright. Just like this negative on the DI told me that this was virtual. Now, what about the HI? Well, it's the HO times the magnification, and so it's 3 centimeters times +1/3, and that looks like that's 1 centimeter. Positive. Positive on that also tells me that it is upright. Now, the last part, because 1 centimeter is smaller than 3 centimeters, I can see that this is a reduced image. I knew that was coming. I saw the picture. So you can see from all of that that the object is, or the image is reduced, smaller than the original. It's upright, it's pointing in the same direction as the original, and it's virtual, meaning that number one, it's formed by imagination. Number two, it's on the other side of the lens than the person was. Before we go, can I show you just how that's always going to be the case with the diverging lens? And so I found this nice simulator over here at our friends at O Physics, and they have, this is their concave and convex lenses simulator, and I'll put a link to this in the notes. This is a great site. Whenever you start off, you end up starting off with a convex lens like this with a positive focal length. You'll see that in my next video. Now you can take this focal length and you can move it around. You move it around to the other side, and there you have it. It will turn a negative, as we just got done saying, that convex lenses have negative focal lengths, and here we have our image. You can see they do a nice job. They draw the parallel ray out parallel and then out as if it come from the focal point. They draw the chief ray. It goes right through that vertex and keeps on going, and then they draw the focal ray. They go towards the other focus but stop at the lens and then go out parallel. And now look, I can move this object around, and there's a lot of similarity between what I'm showing here and what I showed with the convex mirror. No matter what I do, I can mess around with the focal point. I can mess around with the height of the image. I can mess around with the DO, but no matter what I do, I'm always getting a reduced image. It's always virtual, and it's always upright, and that's what this mirror is always going to give you. So keep that in mind. That's what you're always looking for with an image on this kind of lens. And before we go, did you hear about that man who got hit in the head with a can of soda? Luckily for him, it was a soft drink.